Once the pressurizer pressure or level reaches a certain set point, the core makeup tank activates. It's driven by off the, I believe it's off the hot leg of the reactor. It drives pressure into the core makeup tank to drive additional cooling into the reactor. At some point, the in-reactor water storage tank has a heat exchanger in it, and that activates to provide the actual passive core cooling for the core. Once the CMP drops to a certain level, we have depressurization. We have a set of valves that we depressurize into the in-reactor refueling water storage tank. And once we reach 700 pounds gauge, the accumulator or core flood tank. And this system continues indefinitely. So the core cooling and the removal of decayed heat continues indefinitely. Okay, so that's the passive core cooling system. Now, obviously, all of that heat that's put into the containment needs to be removed from containment. That's done through the passive containment cooling into the ultimate heat sink, which is the atmosphere. So the cooling involves the passive containment cooling water storage tank, which is the large tank at the top of the containment. It gives AP1000 its very unique profile of the water tank at the top of the containment. And that interfaces with the in-containment passive core cooling system, because as water condenses inside the containment, that's channeled back into that large water storage tank in containment. And I'll demonstrate that here. So in normal operation, outside air is taken in through the baffles, the inlets, and the outside through this containment structure and cools. And through natural circulation, it cools the containment building and removes heat from inside containment and to the ultimate heat sink, the atmosphere. In the event of an accident with additional energy released into the containment, the cooling provides condensation and condenses the moisture inside containment, reduces the pressure, and at a certain point, if the pressure is increased too high, the water from the storage tank at the top of the containment is released to provide additional cooling for the containment to release the heat for the ultimate heat sink. There's enough water in the tank at the top of the containment for about 72 hours. After 72 hours, other sources of water are available to refill the storage tank at the top of the containment. We'll go over that one more time. This one goes awfully quick, so let me do it one more time. So outside cooling to normally cool the containment through normal operation. An accident releases mass and energy to the containment. Natural circulation continues to cool it to the extent that it can. If the accident is such that the natural circulation, air does not cool it, water is released from the storage tank at the top of the containment to provide additional cooling to remove the heat from the containment and maintain the pressure below the design pressure of the containment. What does all this result in? What it results in is a level of safety that was unachievable in Generation 2 reactors. If we look at the chart on the left, the current NRC requirements, this is based on core damage frequency. There's many measures of safety. This is just one measure of safety. But core damage frequency, 1 times 10 to the minus 4th. The current plants, which of course meet those requirements, about 5 times 10 to the minus 5th core damage frequency. This has been on an annual basis. The U.S. utility requirements, a number of years ago, the U.S. utilities got together and put together a requirements document of what they wanted to see in future plants. Their requirement was 1 times 10 to the minus 5th per year. And the AP1000 results are 5.1 times 10 to the minus 7th. So a significant level of improvement, significant improvement over current plants, current requirements, and even current U.S. utility requirements. Now, these levels of safety, as I mentioned before, can be achieved in other ways. And I'm not saying that only AP1000 can achieve those. we just achieve it in a passive manner as opposed to an active manner. Let me turn to licensing for a minute. We are involved with many licensing activities and agencies around the world. Obviously the United States, the United Kingdom, here in India, throughout Europe, of course China, where we're building reactors. So we have significant licensing interaction experience throughout the world. AP1000 was first certified in 2006. And DCD, you might hear that referred to often as a design control document, and that sets the design basis for the reactor design. And revision 15 was the initial certification of AP1000 in January of 2006. So subsequent to that certification, new rules were brought about, particularly as a result of aircraft crash regulations. And so, because of that, we had a reinforced concrete containment. We judged that would not stand up to the aircraft crash requirements, so we changed our shield building design to a sandwich steel and concrete structure to resist the aircraft crash loads. And so as a result of that, we went through a series of revisions to our design, and our latest design, called DCD-19, was just approved. The final safety evaluation report was issued by the NRC in August of this year, and final rulemaking on that should be later on this year, or at best, at worst, late next year. In addition, the 2 reactor plants in the United States, Vogtle in the state of Georgia and BC Summer in the state of South Carolina, have applied for their combined operating licenses. And those hearings, particularly the Vogtle hearings, just ended this week in Washington. I don't have any specific feedback, but I believe there was no contentious issues in those hearings. And the hearings for BC Summer will occur in the next several weeks. And based on the current schedule, the design certification should be issued this year, and the combined operating licenses for both Vogtle and BC Summer will be issued early in the new year. So good progress in the licensing front. Let me turn to a little bit about construction around the world. Right now we're building 4 AP1000s in China, 2 at the Haiyan plant closer to Beijing, and 2 at the Sanmen plant closer to Shanghai. I'll have some photographs in a minute to show progress, but good progress on those units. And Sanmen 1 is scheduled to go operational in just a little over 2 years from now, November of 2013. First concrete was poured in 2009, March of 2009, so we're a little over 2 years into the construction and a little more than 2 years to go until commercial operation. In the United States, there's 6 units that are committed for AP1000. 4 are actively involved in the combined operating license and are actively under site preparation. That's the BC Summer plant in South Carolina. There's already 1 existing Westinghouse 3-loop plant at that site. And then at Vogtle in the state of Georgia for Southern Company, there exist 2 Westinghouse 4-loop plants at that site, and we will add 2 AP1000s. And then in the state of Florida, Levy County is currently under suspension. So 2 active sites, 4 reactors in the United States, in addition to the 4 reactors in China under construction. So if we look at the China projects, as I mentioned, November 13, commercial operation date. In each of the successive units at Haiyan 1, Sanmen 2, and Haiyan 2, about a 6-month spread between each of those. So by March of 2015, we will have 4 AP1000s in operation in China. In the United States, the commercial operation date for Vogtle 1 Vogtle 3 and BC Summer 2 is April of 2016. So about a year after all 4 operational reactors are finished in China, the U.S. reactors will be starting up. A little bit of just a few photographs. This shows first concrete. I mentioned Sanmen 1, March of 2009, and then the successive Sanmen 2, Haiyan 1, and Haiyan 2 Each concrete pour was a little quicker. We learned a lot of lessons, and we will continue to learn many lessons from the construction, since this is a very unique construction plant relying on modular construction. This actually shows one of the modules. This is the heaviest module. This is the auxiliary building. It's about 1,000 tons that is built in segments in a factory, in a module factory close to the site, is then finished assembly in an on-site module assembly factory, and then moved into the nuclear island. Another module, this is the whole refueling cavity being loaded as a module. And containment vessel, also modular construction, consists of 4 rings the ring segments are built in a factory, shipped to site, and the finished rings are then completed on site, as are the lower and upper domes. Modular construction is extremely important to this design, and it's extremely important to maintaining schedule. Two benefits we see from modular construction. One is improved quality control, because much of the fabrication is done in a shop as opposed to on site, so you have better control. The other is schedule control, because you can work activities in a factory building modules as you're working construction on site, so you have the ability to catch up. And this chart shows when we first poured concrete in March of 2009, obviously we were on schedule. Within a few months, we were quickly 6 months behind schedule. But we were able, by May of 2010, a little over a year later, we were able to completely catch up that schedule. And we attribute that primarily to the use of modular construction techniques. Okay, the supply chain, just quickly end with a few local impacts. Dr. Iwaki from BAE mentioned yesterday the involvement of local suppliers, and we think it's extremely critical to involve the local supply chain. We have a philosophy of buy where we build, so we intend to engage the local supply chain as much as feasibly possible. And obviously, socioeconomic impact of a reactor construction on site. At its peak, for a 2-unit AP1000, you have about 2,000 people on site. So it has a tremendous economic benefit, particularly in the local area for construction of the reactor. So in summary, obviously we're very proud of the AP1000. Its passive technology, its ability to mitigate design-based events, including station blackout, without the use of AC power. We believe it has superior capabilities. It reduces the risk. And we believe that deployment of these type of Generation 3 inherently safe reactors will be of great benefit, not only to India, but to the nuclear world. And we wish the best of success as India continues to embark on your very ambitious nuclear program. Thank you very much.